5. Please switch on the recording. Yes. So now we start formally. So once again, today's lecture, Learning Physics with Conceptual and Problem-Based Approach, which has been organized by the National Academy of Sciences, India, NASI, Delhi chapter, which is a 10-week course which started on 27th of July 2020, every evening from 5 to 8 p.m. It will be also available on YouTube channel of NASI Delhi chapter. So for the students who are sending us continuous inquiries regarding where can the lectures be found, I request all of them to subscribe to the YouTube channel of NASI Delhi chapter. Today's first lecture will be on electromagnetic theory, as we have already started this subject since yesterday. The topic today would be polarization, and the speaker today with us is Dr. Sanjay Kumar from St. Stephen's College, University of Delhi. Dr. Sanjay Kumar has done his graduation and post-graduation from University of Delhi, and his doctorate is from Purdue University, USA. He has about 25 years of teaching experience, and as far as I have known him over the past few years, he is an extremely affectionate person as far as disbursing of the information is concerned, and he is having a lot of experience with what a student requires and how a student feels and how a student requires guidance in any particular subject. His expertise is not only in electromagnetic theory, he is well versed with all the subjects that are being taught at the BSc level. So I welcome you, Dr. Sanjay, once again, and I request you to start your presentation on polarization. Thank you so much.
Thank you, Dr. Verma and Dr. Bindal, for giving me this opportunity to speak on such a wide canvas, where I guess at the moment around 250 students are there. And I must also thank NASI for providing the support for this endeavor, which actually is needed at the moment. I know some of my students who have been basically quarantined in their home for the past nearly 4 to 5 months. It is a time of tremendous stress for young people. They can't go out. And NASI providing this opportunity for them to get back to academics, not in the regular classroom fashion type of way, but academics, which is a different form of selected lectures on a few topics that I think should be a welcome break from this corona pandemic for all the young students. And it's also very interesting that so many young people have actually joined. So it says that, there is interest for theoretical physics among young people. So the future of physics in India would remain bright. There is one person who has raised hand. So how do we handle that?
We shall handle it. Just a second.
All right. Just is my voice level sufficient, or should I?
Yes, it is sufficient. Yes, it is sufficient.
All right. So what I'll do now, I will start today's presentation on polarization of electromagnetic waves. So let me share my screen with this guy, with you people. Okay, so we're going to talk about polarization of E and M waves. And basically, today and tomorrow, we will cover 4 topics. A representation of polarization states. We'll discuss only one way to represent them, but also indicate that there are more than one ways. And in fact, the way which we will discuss is very elementary and simple. And in advanced level physics, that is not the way states are represented, but we will not go to the advanced level. We'll just do the basics. Next topic would be propagation of E and M waves in an isotropic media. And we will see that in isotropic media, just the equations, Maxwell's equations, lead to some very, very interesting results, which are almost unexpected. And then we will, so these two topics we'll try to cover today. And tomorrow we'll apply whatever we learned today to what are a class of crystals called the uniaxial crystals. And then we'll also discuss some polarization devices where, specific kind of devices are used to create polarization of light in particular. Okay? And these are the few textbooks which are very useful. Principles of Optics by Born and Wolf is a treatise. It's a tome, almost 900 pages thick. It is very advanced, but there are certain sections in this book which are very useful. And in today's presentation, we would be using, certain derivations from this book. Then two other books for polarization are which are very useful, very readable, are Eugene Heck's Optics and Professor Ghatak's Optics. So my presentation basically will be closely following, different topics given in these three books. So let's see what is polarization, why, and in what context it arises. Now, this thing you would have learned in your school physics itself that...
Dr. Sanjay?
Yes?
The students request you to be slightly louder if possible.
Louder, okay.
Probably you can move closer to the laptop or use a mic or just be a little bit louder.
Yes, I would then, yes, I will, in fact, okay. So, in school physics itself, students are transverse waves. And the meaning of that is that if you look at the direction of propagation, which is in this diagram is along the z-axis, then the oscillations, the physical quantity which oscillates, and in the case of electromagnetic waves, these are electric and magnetic fields. So the quantities which oscillates, their oscillations are in the plane which is perpendicular to the propagation direction. So that's the idea of transverse waves, and E and M waves, electromagnetic waves, are transverse. This can be proved from Maxwell's equations. Okay? So we won't go to the proof, but this is we'll borrow from it. Okay? Now, given that these waves are transverse, a certain thing happens. Okay? Typically, in most of the diagrams, as in this diagram, what you notice is that the electric field is oscillating, okay? But it is oscillating in the x direction. So it has positive value here, it gets maximum here, then it gets negative x direction, and then again positive x direction. So the electric field is oscillating, but it is oscillating only along a fixed axis. This is normally what you notice in most of the diagrams. Okay? This actually is a very, very specific state of oscillations of the electric field or magnetic field for that matter in EM waves. See, actually, all that Maxwell's equations tell you is that these fields should be oscillating in the plane perpendicular to the propagation direction. In that plane, it's not required that they should be oscillating in a fixed direction only. They could be, the direction of the oscillations could be changing with time. So when you talk about the polarization states of an EM wave, we are generally dealing with situations in which the direction of oscillation of electric field or magnetic field, those directions themselves could be changing in the transverse plane. So that's something which you actually happens in the, which you actually get from the Maxwell's equations. And that general situation produces different states of polarization. So polarization as a physical concept refers to what is the state of oscillation of the electric field or magnetic field in the plane perpendicular to the direction of propagation. So this is what we already discussed, that we require the fields to be perpendicular in a plane perpendicular to the direction of propagation, but within that plane they could be oscillating in all kinds of different ways. Now let's see. Here what you have is a wave which is a harmonic plane wave. and monochromatic. And everybody knows the meaning of monochromatic wave, that it has only one frequency. Okay, and what could be the meaning of plane wave? Okay. Now here, notice that we're writing electric field. It's a vector quantity. So what you have done, you have decomposed a vector field into two components. So this is, like component along x direction, component along y direction. Now, why we are calling it plane wave? We're calling it plane wave that the variations of electric field as far as space coordinates are concerned, they are only function of the coordinate z along which the wave is traveling. There is no dependence on x and y. What it means is that if you pick any point which has same value, or if you take all the points which have same value of z, but the values of x and y could be different. So you're talking about a plane, xy plane, and you can move it parallel to z-axis plane. The value of electric field or magnetic field will be same at every point. Okay? So the electric field in this case does not have any dependence on x and y. That's what makes it a plane wave. So irrespective of any value of x and y, electric field has the same value, which means that if you take a surface of the constant phase of the wave, that surface would be the xy plane. So that's what makes it xy plane. So there's no x and y dependence. Now we're calling it a harmonic wave. Harmonic wave means that the dependence on space and time coordinates is through harmonic functions, namely sine or cosine functions, or the combinations. Now here we're writing in look at the argument of the cosine function here. So it's kz minus omega t, which means that if you have a particular combination of space and time like this, it's a very specific combination. Your argument of the cosine function is not made up of separately of position, namely z, and separately of t. Z and t occur in a very, very specific combination. And it's that combination which makes it a traveling wave. And in this particular case, since the sign is negative, this wave is traveling around positive z axis. So this is a traveling one particular dependence of the x component dependence, and this is the j component dependence. And what we have done here, if you look carefully, we have x and y components, they have different amplitudes. Furthermore, they also have an additional phase difference. So we just written down the y component as a phase difference with respect to the x component. Otherwise, the harmonic dependence, like this is the wave number and this is the angular frequency, those are the same in both the components. That's what will make them monochromatic. So what you have done is you've written down electric field as we have decomposed it along two orthogonal perpendicular components in the plane, which is perpendicular to the direction of propagation. Now, what we want to emphasize here is this is the particular representation of states of polarization plane perpendicular to propagation. We're calling those orthogonal directions just an x and y. And any state of polarization can be represented by can be given by different combinations of the amplitudes. They have absolute values, but the ratios of the amplitude and this phase difference that produces all possible states of
Dr. Sanjay, your voice is breaking, and
so this is the specific representation which I mentioned that we will talk about.
Hello.
So let's now proceed. You would have heard, hello, yes.
Dr. Sanjay, your voice is breaking. Please
Outside,
check your network. Just please check your network if it can be switched to Wi-Fi.
Yes, I'm checking it, and it did mention that there was some problem. In fact, it's raining outside, so it may be the.
Yeah.
I'm
I
closer.
request the students to have patience. When you are writing something, we will attend to it. And this everything is based on network. So sometimes there might be some problem. However, now it is back to normal. And I think, Dr. Sanjay, please continue. Thank you so much.
Yeah, what I'll do, I'll switch off my video so the band requirement from my
Yeah,
side.
yeah. Okay, that's fine. Yeah, that
Should,
is fine. That is fine.
that should.
Absolutely fine. Yes. Thank you so much.
To unmute myself. Okay. So plane polarized EM waves in the sense I'm getting muted again and again. Let me see. Am I audible now?
Dr. Sanjay, this happens because of network problem. We faced it also with another speaker. It's not from our side. So you would have to kindly look at the mute button. And if you
Yeah,
get
I'm
muted, you
unmuting
will
it
just,
again, but it just gets muted.
yeah, that's when the network will be
I'll keep on
stable,
doing
it
it.
will be stable.
I will keep an eye on the mute button. Okay. All right. So plane polarized is easiest to understand, at least visualize, because electric field is moving. Now, in our representation, which in the two orthogonal directions, the plane polarized lights can be created by picking up particular values of the phase difference, and 0 plus minus pi plus minus 2 pi. So basically multiples of pi of phase difference produce plane polarized light. That's very simple to understand. Okay. So what you have done here is, if you pick, for instance, in that equation, if you go back, we had epsilon in one of the component. If that is 0, then of course you can bring that, the common factors out. You have cosine kz minus omega t from one term if the phase difference is 0, and minus cosine kz minus omega t if the phase difference is pi. So this is plus corresponds to phase difference 0 and minus corresponds to phase difference pi. Okay. So we can very easily see we have now the electric field oscillating in a direction which is determined by this vector. Remember, this is a vector. Okay? And this vector is in a particular direction. So electric field actually is oscillating only in this direction given by this vector in the bracket. Now this is a diagram which is, which shows you, in this particular case, this is EX, this is EY, and they both, well, in this diagram, they happen to have the E0X and E0Y have the same value. And so the direction which this vector will produce with plus sign would be in this direction. So basically, electric field is oscillating in this direction. This is, as you know, is a plane polarized light. Now, if you had taken epsilon equal to pi, then you would have a minus sign, and then the oscillations would be in this direction. All right. So this way, you can create plane polarized light. Now, in these diagrams, since at least what is shown is that the oscillations are either, with, let's say, a 45-degree angle with the x-axis or 135-degree angle with the x-axis. But you obviously know that plane polarized can be in any direction, doesn't have to be these 45 degrees angle. So what can be, how would you produce oscillations in different directions? Well, for that, all you need to do is to look at the ratio of E0Y and E0X. So the angle which these oscillations make with the x-axis, that is given by the ratio of these axes, ratio of these amplitudes. So this way, by picking, the phase as a multiple of pi, and by picking different ratios of the amplitudes, you can represent any plane polarized light in the representation we are talking of. Now let's proceed. The next level of complexity in the polarization is what is called a circularly polarized light. And that is created by picking the phase difference as multiples of half pi, okay, odd multiples of half pi. So you have pi by 2, 3 pi by 2, 5 pi by 2, and all the plus and minus signs are there. Okay. And what you also remember, note to do, I forgot to write on here, that the amplitudes E0x and E0y should be same. Okay. So with that, E0 is common factor. Okay. And if you take, for instance, put epsilon is equal to pi by 2, you can do the expansion of, cosine A plus B. And so that gives you cosine kz minus omega t plus pi by 2 gives you a sine function. Okay, so that's what you get here. And what kind of oscillation does this represent? Okay, and now to do this, what you can do is either you can look at it at z equal to 0, because that's the simplest. Otherwise, z just keeps on hanging, or you have to keep some fixed value of z. So if you take z equal to 0, then look at this. Now, I'm sure that you know, even from your school physics, that this quantity here, this vector, okay, it's a vector quantity. We have I and j unit vectors, but the value or the components of along x and y axis, that's not constant. They are oscillating like sine and cosine functions, and there's a phase difference of pi by 2. One is oscillating like sine, other is oscillating like cosine, and that is a circular motion. And circular motion can take two directions. It can be clockwise or anti-clockwise. This in particular is a clockwise circular motion. Oh, sorry, anti-clockwise circular motion. Because as t is increasing, if you can start with less t equal to 0, then E vector would be along the x-axis, and as t increases, both the x-axis component will decrease and the y component will increase, so it will be increasing, it will be moving counterclockwise. Okay. So we get counterclockwise rotation by picking epsilon equal to pi by 2. And by now you can very easily guess that if you had picked epsilon equal to minus pi by 2, you would have gotten a clockwise rotation. Okay. So this is a diagram I have taken from Hecht's book, which shows how a clockwise rotation of the electric field takes place in the plane perpendicular to the propagation direction. Okay. So let's say at t equal to 0 or some axis, this is the reference direction. So this would be the x and okay, these are the x and y components. Okay, and the rotation, if you write down pi equal to minus pi by 2 in that expression, it will be going like this. Now, what you have to physically understand what's going on is that if you focus on one particular plane, xy plane, of z, then the tip of the electron is moving around in a circle. Okay? And this is happening at every point in the space. So that is what circularly polarized light is. And you can characterize a circularly polarized light by its amplitude and whether it is going clockwise or anti-clockwise. Now, when you mention clockwise and anti-clockwise, you have to be specific. In which direction are you looking? So the convention is that you look back at the source, meaning you look back in the direction opposite to the direction of propagation. Okay. So if the light is propagating, let's say, suppose this is the z direction, then you will be looking back against the axis towards the negative z direction. So you look at the source from where the light is traveling, and then notice in which way the electric field is rotating, if it's rotating clockwise or anti-clockwise. And the convention is that if it is rotating clockwise, we call it right circular polarized. And if it is making anti-clockwise, we call it left circularly polarized. So polarization state, circular polarization states are further divided into right and left circular polarization, depending upon in which direction is the electric field oscillating. Now, the next thing is elliptically polarized light. Okay? And for that, what you do is we keep the phase difference and these amplitudes arbitrary.
So they can take any value. Okay? So elliptically polarized in that sense is the most generalized state of the polarization. And the other states, namely circular polarization or the plane polarization, they are special cases of the elliptically polarized light. Okay? Now, how do you notice that this is, will produces an elliptically polarized light? This is a derivation which many of you would have done in your Lissajous figures experiment, so we won't go into details. But what you essentially do is you can manipulate these two equations. And what you do, you manipulate so that you eliminate the space and time dependence. Okay, for instance, you can write down cosine kz minus omega t as ex by ex divided by e0x. Okay, so you get an expression for cosine kz or minus omega t. And once you have an expression for cosine, you can also create an expression for sine. Okay? And when you go to this equation, you can expand this function into cosine kz minus omega 2. So this is cosine a plus b. You can expand this also into cosine and sine functions and then use the values of the two from the first equation, put it here, that will be, you'll be able to eliminate the space and time coordinates and you get an equation like this. Now, what is this equation? It has the values of ex and ey. Okay? These are given here and they can change. And other parameters here are basically constant. So E0y is a constant, E0x is a constant, epsilon is a constant. Okay? So this is then an equation which links EY and EX, which means EY and EX, remember these, EY and EX, they are not independent of each other. There's something connecting the two. And when you have two variables independent of which are connected by an equation, you get a curve. And the form of this equation is the form of an ellipse. Okay? That's why we call it an case of elliptical polarization. All right. Now, what we have shown here is for a general expression like this, what would be the behavior of the electric field vector in the plane, again perpendicular to the direction of propagation. So for this kind of expression, remember Ex and Ey are components of the electric field, okay? And these components, they have harmonic components we are suppressed because, this is just the value of Ex and Ey, but they will be then multiplied. They will also have these, the harmonic components. So this vector actually is rotating with the frequency omega in the plane so that, at any given moment, you'll get the value Ex and Ey. But it's rotating in such a way so that the tip is basically a and basically an ellipse. Not in is basically drawn in a coordinate system which has Ex and Ey. All right. These are not space, though they are directed along the x and y direction, but keep in mind, these are the coordinates are Ex and Ey. These are not the space coordinates because this is a vector E. This is not the position vector. Okay? Now, what you notice is the size of the ellipse, which is a semi-major axis, the ellipticity given by the semi-minor axis. So these two axes, they are determined by E0y, E0x. And the orientation. So this ellipse is basically tilted with respect to x and y axis. Now, in coordinate geometry in your school physics, you would have dealt with ellipses, which are symmetrically placed along x and y axis. This is a more general representation in which the ellipse is tilted. It's a slightly more complicated representation. We won't go into it, but the idea is that this tilt, this alpha, which is very important, that one can get by in terms of the amplitudes E0y, E0x, and cosine epsilon. Actually, this should have been E0x. There's a mistake here. So if anybody is copying, make it E0x. So depending upon the phase difference and the relative amplitude of x and y direction, there would be this angle. And we can very easily see, if epsilon is, for instance, pi by 2, alpha goes to 0, this thing will be, the semi-major axis would be along the x-axis. Okay? So one can work out different orientation of the ellipse by picking different values of the epsilon. So this is the representation for the elliptical polarization. Now, there's something else you have also heard about. You have heard a lot about the unpolarized light. Okay. In fact, most of the natural light which you get from natural phenomena, like from sun, for instance, or even technology objects like incandescent lamp, etc., are unpolarized light. Okay. Actually, it's better to call it randomly polarized light rather than unpolarized light. Why we're saying randomly? Because at a given moment, that light also has a particular state of polarization. But what happens is that its state of polarization is changing randomly with time. Okay, that's what makes it a randomly polarized light. So if you were to trace what is the electric field at a given moment in the plane perpendicular to the propagation direction, you will get a particular direction of electric field. Okay, but that direction is changing randomly, and the magnitude of the electric field is also changing randomly. So how would you create a randomly polarized light? Well, the amplitudes of the two orthogonal oscillations and the phase difference, that these three parameters, when they change randomly in time, that creates a randomly polarized light. So that is the way, that is how one can present a randomly polarized or unpolarized light in our in this representation. Okay? Now, this is a very interesting point, which is not commonly realized, but those of you who will continue with physics and do quantum electrodynamics will notice it later. See, actually what happens is that even though now we are represented different states of polarization in terms of two orthogonal x and y directions of electric field, but actually we can pick any two orthogonal polarization states, and it turns out that the left and the right circular polarization states are also orthogonal states which are perpendicular in some way. Okay, we're not defining orthogonality very precisely, but keep in mind that they're perpendicular in some way, and all other states can be represented in terms of left and right circularly polarized light. Okay, so that would have been an alternate representation. Okay, and it's very simple. Suppose you take EL is a left circularly polarized light, ER is a right circularly polarized light. We have expressions for them in the earlier slide. If you just add the two with a zero phase difference, okay, what you would get. So this is what this is, left circularly polarized light. This is right circularly polarized light. The phase epsilon is kept zero, so all you notice is this difference of sign. So naturally, obviously, you get this. This is a plane polarized light. This is a light which is whose electric. This is plane polarized EM wave whose electric field is oscillating only along the x direction. It's harmonic, that's fine, but it's oscillating only in the x direction. So simply by adding, plane right circularly and right circularly, left and right circularly polarized light, you can create a plane polarized light. Now, you can similarly do for an elliptically polarized light. So this is a diagram which has showing you two circularly polarized lights. So this is one circularly polarized light. Okay, so electric field is going around on it. The tip of the electric field is moving harmonically on a circle, okay, which is counterclockwise. And then second is this one, okay, which is a clockwise. What you have is that the two of them are different amplitudes. Okay. All right. And what happens is that this produces, if you add the two at a given moment, EL and ER at a given moment, what you get, if you keep on adding, you get an ellipse. All right. So this way, by adding to a left circularly and a right circularly polarized light, you can also create an elliptical polarized light. This would have a phase difference also, as well as different amplitudes. Now, this is the important thing, which is physically significant. That if you were to do the quantum field theory, okay, not the classical theory, but in quantum field theory, the quanta or the energy packets of electric and magnetic fields are what are called photons. Okay, and some of you have done quantum physics, so you would understand what is the meaning of eigenstates, etc. So we'll not go into it. But the point is that the photons in the quantum field theory, they are either left circularly polarized or right circularly polarized. Okay. So according to quantum field theory, according to physics actually, the right circular and left circular are more fundamental than our representation along the orthogonal direction. But that's of course the mathematics is slightly more complicated. That's why we didn't go that way. But keep in mind that what you have discussed is only one representation of the polarization of light. And actually more complicated would be using circularly polarized light. Now I'll leave that as a question. And this question deals with the problem in the previous page. Remember in the previous slide, if I go back, let me go back, we got a plane polarized light by adding by adding a left circularly polarized light and a right circularly polarized light. But notice that this is only along the x-axis. Suppose you want polarization not along x-axis, but in some arbitrary direction. Okay? At some angle, let's say alpha or phi with respect to x-axis. How would you add a right and left circularly polarized light to get plane polarized oriented in an arbitrary direction? So that's a question you need to think about how it can be done. Think about it, how it can be done. And I won't solve it, but I will leave, for you to certain problems and solutions. I will leave, I'll distribute PDF files so you can go through them later. Now we move on to the second topic, which is propagation in anisotropic media. And why we're doing it, the reason is the following. Because polarization states, we discussed different polarization states, plane polarized states, circularly polarized states, elliptically polarized states. These different polarization states, typically, they are produced with the help of anisotropic medium. Anisotropic basically means that the property of the medium in different directions is different. Okay? And the prime example of anisotropic medium are crystals. Some of you would have done solid state physics course, in fact. Yes, some of you would have done solid state physics course. So you know that crystals are very specific arrangements of atoms in solid state, and they are anisotropic, because if you look in different directions, the crystal does look different. Okay? And we will see that when EM waves, particularly light, when it travels through crystals, it develops very specific polarization states. That's the reason why polarization is very closely linked with the propagation of EM waves in anisotropic media. Okay. So anisotropic media are the prime means to generate different states of polarization. That's why you want to study. Okay. Now, what happens in isotropic media? So this is a very simple diagram I have drawn to see how anisotropy is created. Okay. So this is a molecule. Okay. In this case, it's an ionic molecule, but it could be some other molecule. Also doesn't matter. Okay. Now there is a bond. And bond is a directional thing in space. So there's a bond direction here, let's say going in this way. Okay. If you create an external electric field, let's say in this direction, okay, then the charges in this molecule, electronic charges in particular, they will be redistributed. Okay. So for instance, the positive charge will tend to go in this direction, negative charge will tend to go in this direction. What that will do, it will induce a polarization in the molecule. And that happens in any circumstances. Whatever atom you take, whatever molecule you take, when you put an external electric field, there would be some polarization. Okay? But what we need to notice is that because there is a direction of a bond here, the motion of the charge due to external field is easy in one direction and more difficult in another direction. So there could be, easy directions of polarization and difficult directions of polarization. Now we're using the word polarization, the same word which was discussed earlier, but please keep in mind this polarization and the polarization which we discussed a moment ago are very different. That polarization refers to the state of the oscillation of electric field in an EM wave. Here, you're not talking at this point, at least, of any wave. All you're doing is how much dipole moment is induced when you produce a molecule in an external electric field. So this P refers to induced dipole moment. Okay, just the separation of positive and negative charges. So the idea is that if electric field is along the bond length, bond direction, then there will be greater polarization. On the other hand, if electric field is in some other direction, in this case, for instance, perpendicular to the direction of the bond, then the polarization P developed will be less. So there are easy directions of polarization and difficult directions of polarization. Okay. Now, if for instance, you put an E in some arbitrary direction, of course, you can break up into two orthogonal components, one along the easy direction, other along the, let's say, difficult direction. Okay, one like you can break up any E in any direction. Suppose E is along this, so you can break up into this direction and this direction. Now, the induced polarization would be more comparatively in this direction than in this direction. Okay. Now, what's the consequence of that? The consequence of that is that for an arbitrary E, the induced P is not parallel to E. Now, this is something you would not have learned in your first year physics course, where you do discuss polarization. There, in fact, we assume that the medium is isotropic and linear. So here we are dropping the isotropic condition. We are saying that polarization, induced polarization, can be different in different directions. Okay? And one consequence of that is very easy to see that E and P are not parallel to each other. Okay? So you have electric field, the induced polarization can be in different direction than the electric field. So that is what is important here. Now what it does is that our expression which you use for the linear isotropic medium, that P and E are parallel, that does not hold true. Okay, that doesn't work. Okay. So when you go to electric displacement, you would have seen in your first year physics, when you discuss, electric fields in medium, we have to introduce introduction of something called electric displacement simplifies the equations tremendously. So we're just borrowing that definition. This is something which is made up of electric field present as well as the polarization. Okay? So it's a particular combination which simplifies the equation of electrostatics and electrodynamics. So since E and P are not parallel, it means D and E are not parallel. Okay? They can be in different directions. Now we have a concept which you need to understand. That concept takes you to the idea of tensors. So we'll spend some time here because tensors is something which many of you would have been introduced only this year. So, it's very good to get accustomed as many tensors as possible so you get a better hang of what's going on. So we'll spend some time on trying to implement this idea that D and E are not parallel. Okay. So what's going on here? See, we have two vectors, D and E, right? Now, what we want is that this D vector depends on, in some way, on E vectors, okay? And different components of D, they depend differently on E. That's what will create, if the components were proportional and proportionality constant was same, D and E would be parallel. We don't want that. Okay? We want D and V to be not parallel, which means different components of D is a linear component of E, but its dependence, linear dependence of a component of D on E is different for different components. Okay? All right. This means something like this. So we have, for instance, the first component. One stands for X component. So D1, it depends linearly on the three components of E, and this coefficient which determines the dependence can be different. Okay. You could similarly have D2. Now the dependence of D2 on E1 would not be E11. That would be some other constant. We'll call that constant E21. Okay, all right. And then there'll be another constant dependence of D2 on E2 would be epsilon 22. Okay. So actually, if you think about the three components, which depend on three components of E, and the coefficients of every component of E in principle can be different. So we have actually 9 different values of these linear coefficients. Okay. And a physical object made up of these nine different values is what we call permittivity tensor. We'll come to that in a moment, but you get an idea how this idea of tensor is made up of quantities here, which are not 3, which are 3 cross 3 or 9 different values. Okay? So this is a representation of the dependence which you want to show of D on E. Okay, these are 2 vectors and their different components. But we want to represent equations like these. There will be 2 other equations, D1, D2, D3. We represent in a compact way by this equation using tensor notation. So epsilon Lm now stands for the permittivity tensor. And look at this equation very carefully. You will have, summation over M. And M goes from 1 to 3. So if you take, suppose you want this equation. So what you'll do, you'll put L equal to 1, right? And then you have epsilon 1, M equal to 1, epsilon 1, 1, E1. Second term would be M equal to 2. You get epsilon 1, 2, E2. Third term would be epsilon M equal to 3. You get epsilon 1, 3, E3. And similarly, you can take L equal to 2 and get the second component and the third component of T. Okay. So this is a very compact way to represent the kind of dependence which we have. Okay. Notice it's a dependence which is linear dependence, but the components of 2 vectors are dependent on each other. Every component of one vector depends on all other components of the other vector, and dependence can be different for different components. That's what we're putting into it. Okay. And that creates this tensor. So some of you who are mystified, what this object tensor is, keep this kind of very simple linear relations between 2 vectors in mind. Okay? And a tensor relates 2 different vectors in the most general way that they can be related. Most general, but still linear, because these are constant coefficients and you have single powers of the components. You don't have square roots or squares. That would make it non-linear. All right, so this is our definition of permittivity tensor. It occurs in the relationship of electric displacement with electric field. And as we argued earlier, since D and E are not parallel, we have to have this tensor representation here. Okay, so let's proceed further. So we argued that this permittivity tensor, which occurs in the relationship between electric field and electric displacement, it has to have 9 components. Okay, it's 3 cross 3 tensor. But it turns out that there are a number of constraints on this tensor, which reduces the number of independent components. Okay. Now this is slightly tricky derivation, so we'll again go slow, and let's see what I do here. Okay. So we start with the electric and magnetic field energy densities. Okay. So these are the definitions of UE and UM. These expressions would have been derived earlier, so we're not going to derive them here. We're just going to borrow. So we have half of E dot D. Now what we do is, for D we put the tensor representation in terms of E. Okay, first of all, that's the next step. The first step is writing just E dot D. So what is E dot D? E1 D1 plus E2 D2 plus E3 D3. Okay, and that sum you can write down like this: summation L going over 1, 2, 3, and EL DL. So L is equal to 1, you get first term. L equal to 2, you get second term. L equal to 3, you get third term. So this is the way to represent a dot product. Now for DL, we put the representation in terms of E using the permittivity tensor. Okay, so dl, if you go back to the earlier slide, was epsilon m em. So now we have here actually a double summation. Summation over L is coming from the dot product, and summation over M is coming from the definition of B in terms of electric field. So both L and M are summed over. In general, when you have a dot product of vectors, it will not have what is called any free index. We'll just have a sum or a double sum, and there will not be any, all the values of 1, 2, 3 will be summed over. We'll write down E dot D. Okay. Now, this is the expression for magnetic field energy density, half B dot H. And here we are assuming that as far as the magnetic field properties are concerned, the system is isotropic. It is same in all the directions. So H is basically, this auxiliary magnetic field is basically B by mu. So B dot H give you B square by B. Okay. So here the assumption is that magnetic properties of the substance are isotropic, just to simplify the mathematics. Okay. Now we come to a very important result, which goes by the name of Poynting's theorem. I don't know whether, well, you must have discussed it at least in your regular lectures, but I'll just give you an idea what is happening here. Energy is conserved. Which means that if you take a volume of space and find out what is the energy in that volume, what is the electromagnetic field energy in that volume. And remember, electromagnetic field energy is in terms of UE and MUM. Okay. These are the densities. So if you have a volume, you integrate these densities over the volume, you get the field energy in a given volume. Okay. Now, this field energy doesn't have to remain inside the volume. It can be moving in or out. Okay, so from the surface of that volume, there would be a flow of energy. Energy could be flowing out or it could be flowing in. When it is flowing out, if the volume remains fixed, the energy density should decrease. If the energy is flowing in, then the energy density should increase. So if you got it? If the energy is flowing out, energy density would decrease inside the volume. If the energy is flowing in, then the energy density would increase. Now that is the idea which mathematically can be represented either in differential equation or in integral equation. So let's look at this integral equation for the first, integral expression first, okay? So what you have on the right hand side is basically energy densities, integrated over volume. So we have basically energy in the volume V. Okay? And then you're saying this energy could be changing. So it has a d by dt. Now, if suppose d by dt is suppose it's a negative quantity. Okay? So if this is d by if suppose the energy, this integral d by dt of this integral is positive, but you have an extra negative sign. Okay? So right hand side will be negative. Okay? Then it can be shown that you can write down the energy flow, because whatever energy is leaving, you can write it down as the rate at which energy goes out per unit area. So then you can write down this surface integral. Okay. So this is one way to represent. So the left hand side represents the energy which is flowing out or in from the surface. Right hand side represents the change in the energy contained in the substance. And this negative sign comes, because when the energy flows out, you take it to be positive. But it basically represents the energy conservation. So if there's a change in the energy inside the volume, energy has to either flow out or flow in. Okay, and this flowing out and flowing in is given by this integral s dot dA. S is called the Poynting vector. Okay, and it turns out from Maxwell's equations, this Poynting vector has to have this expression. E cross B. Okay. And so whenever, this is a very interesting result, whenever you have a situation where E and B have non-zero cross product, okay, there would be flow of energy, flow of electric field energy. And you can have a situations, which are very different. Typically, we think about, flow of energy of electromagnetic waves with electromagnetic waves, but that doesn't have to be the case. All you require is that you have E cross B to be non-zero. There would be flow of electromagnetic energy. For instance, you can think of a current flowing in a wire or a cylinder. Okay, you have electric field along the length of the wire, and when a current is flowing, there's a magnetic field. And that magnetic field, E cross B, you can very easily see will be non-zero. Then there will be a flow of energy into the cylinder. Okay, so this is a very, very important physical concept, the Poynting vector. It represents the rate of flow of electric and magnetic field energy per unit area at any given point. So if you integrate it over a closed surface, you get the total energy which is flowing per unit time across that surface. So this is the statement of conservation of energy in electrodynamics. A very, very important result we should keep in mind. Now, let me see how much time we have taken. Well, we are nearing almost 1 hour, so after 1 hour, we'll take a 5-minute break. Now what we do is, once we have cleared this idea of conservation of energy in electrodynamics, how it gets represented in terms of Poynting vectors, let's do some exercise in what we are doing. Okay? So we have a definition of S. Let me go back. Definition of S being this. Okay? E cross B, that's it. Okay? You take the divergence of this. So then you have divergence of two vectors. Divergence A cross B. Okay? And we can use the vector identity for divergence of cross product of two vectors. Along with that, we use Maxwell's equations. There are two Maxwell's equations you use. Del cross E is equal to minus del B by dt, and del cross B is mu del D by dt. Actually, there could be a free current also, but we are assuming there is no free current. So that term is dropped. So there is no actual motion of charges, motion of free charges. So you have these two equations. You put these equations into the divergence of S, and obviously, one of the equations gives you D, okay, and the other equation was basically, B dot B, which you have written down in terms of the magnetic field. Okay, so this is divergence of S. We are just taking the divergence of the definition of S here. Okay, but from energy conservation, we also had another equation. Okay. Which was, if you go back, let's go back to the earlier equation, which was basically this equation. Okay. Delta of UM and UE. And if you remember that equation, UM was already there, UE is an extra term. Okay. And UE is in terms of E dot D. So when you take del by del T, you will get del by del T of E dot D, both of them together. Okay. That's what you will get. Okay. So one divergence S would give you, will have a derivative of both E dot D together. Okay. The other term, which we derived by using divergence of directly, doesn't have time derivative of E dot D. It has E dotted with the time derivative of D. So there is different expressions for the same quantity, namely divergence S. Now, if you compare these two expressions, you get this result. So this is E dot dt, E dot del D by del T from this side, and this term is coming from divergence of S from the energy conservation. So energy conservation basically implies that these two expressions should be equal. Okay. Now what's the consequence of this in terms of what we have been doing? Well, we did write down D in terms of with the help of permittivity tensor. Okay. So this is the expression for the left-hand side. Okay. Again, notice that since you have a dot product of two vectors, there are no free indices. Now we use another rotation here. See, whenever we have repeated indices, so here K occurs twice. Similarly, L occurs twice. Okay. And a rule was, devised by Einstein, which is very simple rule, which says that whenever an index appears repeated, it is implied that summation is taking place. So that's why we have not written down explicitly summation expression. summation of k over 1, 2, 3 and summation over L over 1, 2, 3. Okay. In some textbooks, you might find, the summation sign being written, but the more modern idea is that whenever an index is repeated, summation is implied. You don't have to, put those big sigmas every time. Okay. So here, summation over indices, both k and L is taking place. Okay. So we are summing over k and L. Okay, so we have this expression. What can we do with this? Okay. There's a very interesting mathematical operation when you can do when you are summing over, very interesting operation you can do over summed over indices which are getting summed over. Okay, and k and L are indices being summed over here. So what we do is basically we pick this expression. Okay. Now, if you think about this expression in detail, so you have, k equal to 1. So E1, epsilon 1, let's say L equal to 1 and E1. That will be one term. Okay. Then you have k equal to 1, L equal to 2. K equal to 1, L equal to 3. Okay. So you'll have 3 terms by this. But then we'll go to k equal to 2. K equal to 2 will give you epsilon 2, 1. Okay. And similarly, epsilon 2 would give you epsilon, k equal to 2 will give epsilon 2, 2, and so on and so forth. So it will be there'll be 9 terms in all. But remember, once you have those terms, okay, it's a sum of all these terms. All you need is that somehow that sum should be created. And that sum can be created either writing it like this, or you can interchange k and L. That doesn't matter because all the value of k and L are included in the sum. So if k equal to 1, you will have, that term as the first in one sum. If you put L, then L equal to 1 might be appearing later in the sum, but that doesn't matter. Addition is associative, so it doesn't really matter. So what we can do, this is a very important and interesting operation one can do. We can interchange indices which are summed over. So in this term, we interchange k and L. So this first term then becomes this. Wherever you had k, you wrote down L. Wherever L, you wrote down k. Okay, so this becomes this. Now this is very interesting. All the terms have ek and derivative of En. This and this. Okay. So basically, then that tells you that epsilon KL, okay, has to be equal to this sum. This is now very important here. Okay. We had the sum here, okay, all right, and that sum is valid for any value of these coefficients. Okay, so you can take these coefficients and you take the terms, and the term with these coefficients in all of them are the same. Okay, so they can be cancelled. So you get this result now, which is valid for every value of k and L separate. This is the important. Here it is sum, but here this equation you can have different. You can have any value of k, any value of L, and here you have this result that epsilon KL is equal to the half of epsilon LK and half of epsilon KL. What is the solution to such a problem? Well, the solution is that epsilon KL is equal to epsilon LK, which tells us that permittivity tensor is a symmetric tensor. So physically, before we stop for 5 minutes, what we have done is that we have used the physical idea of the energy conservation, applied it into electrodynamics, and gotten the result that the permittivity tensor has to be symmetric. So instead of 9 components, it will have only 6 independent components. So this is one constraint which will have on the permittivity tensor. Now, after a break, let's take a break, and then we'll other constraints which permittivity tensor has.
Yes, Dr. Sanjay, the students do request for a break after an hour or so. And at this time, if you would like, probably you can read the question answers in the question answer box.
And the chat box, all of them?
No. the question answer
Oh,
Q&A.
question answer. Okay, the 10 of them. Okay, okay. Let me see.
And meanwhile,
Uh,
one announcement to the students, please watch the webinar chat box. You have now the first attendance link. You have now the first attendance link. Please fill up your attendance link. And if somebody is not listening, I'm repeating again, please, there is a first attendance link in your Zoom webinar chat box. Fill it up, and then you will have a second attendance link later on. Please do not fill up your email address wrongly. Yesterday, we had students filling up their email address wrongly. If you do so, you might not be able to get your Zoom link for the next day because your email addresses are confirmed from your attendance. Now, this attendance is open for 15 minutes, and that is definitely sufficient. Please be attentive and fill up the attendance link. Yeah. Yes, sir. Yes, Dr. Sanjay, you can take up the questions
yes, so
one
should
by
I
one.
answer them now? Yes, I can answer them now. Okay.
Yeah, while they fill up, they can keep hearing. It's not a problem. They just have to write
Yes.
their name and email ID.
Okay, okay. Yes. So there's an answer for a question from Manu. The meaning of orthogonal. Okay. In terms orthogonal, the clearest expression of orthogonality which you get is if you take two perpendicular vectors, the dot product is zero. So in that sense, they are called orthogonal. But in advanced mathematics, you basically define a product. Dot product is a particular kind of product. Okay, E dot A dot B, for instance, AX BX plus AY BY and AC AZ BZ. That's a particular definition. In advanced mathematics, you will have a different definition of a product. Okay, and there also, when a particular product of two quantities, it happens to be zero, then we can call them orthogonal. Okay? We have used the fact that right circularly and left circularly polarized lights are orthogonal. Okay? In fact, one can represent these two circular polarization in terms of matrices, and one can very easily see that when you take a product of those two matrices, you get a null matrix. Okay? So there are different ways in which the orthogonality is represented. The problem you're dealing. So that's all I can say. Perpendicular gives you the idea of perpendicular 90-degree angle in space. Okay? But the more general understanding of orthogonality is just taking product in some particular way of two things. And that product will be defined depending upon the context. We can, for instance, talk about product of matrices, and which doesn't have to have any direction. So in that context, when you represent right and left circular polarized light in matrices, in terms of matrices, these are called the Jones matrices. We are not discussing it here, but one can show that those two are also orthogonal. Okay? There's a question by Shruti which I couldn't understand. Is it EX by E0X in the equation? I might have made a mistake, so I'll have to look at if I made a mistake in the expression I wrote. But yes, it was E0X by EX, not EX by E0X. The calculation for tangent to alpha, a fine geometry. This is coming from a very complicated coordinate geometry. I have not done it, and I'm sure some of you can try, but I'm sure it's not an easy problem. It'll take you quite some time to derive that expression. But we just borrow it from whatever mathematicians give us there. Well, there's a question about ordinary ray and extraordinary ray. Well, that is something we'll discuss tomorrow. So wait till tomorrow about how, in certain class of crystals, O rays and E rays are created. Okay. Acha, then people are asking about, which references are you doing? Well, I would, for today's lecture, basically I have taken material from Eugene Hecht's book and Born and Wolf. Okay, these two, basically from these two. Okay, and then of course my own interpretation of other things.
Dr.
Okay, there's a
Sanjay,
yes.
So students are saying that your lecture is extremely good. Many have written that he is amazing. Some have written he is wonderful on email also to me. And they are saying that it's very helpful in enhancing our concepts. please arrange more lectures of Sir on electrodynamics.
So
So I
we'll meet
can
tomorrow
wait with
anyway.
respect to you. You
Thank
can
you.
probably consider maybe sometime in the future you have a little bit more
Okay, sure.
time, and people are saying you're absolutely amazing, and so on. So you have a great fan following among students. So we request you to kindly consider few more lectures whenever you think it's suitable to fit in your busy schedule. Thank you so much.
All right. Okay. Yeah. Thanks. Okay. The other question is Priyanka is asking about energy conservation. Yes, we are assuming there is no dissipation. If you have dissipation, of course, you have to include it, and that will modify the equation which we wrote down. And yes, we are also assuming there is no other transformation. So basically, you're saying that whatever energy is in the form of two things. It can be either contained as the mechanical motion of charges, or it is in the electric and magnetic field. So that's what you're assuming in that equation. So it's completely electrodynamic energy. Okay, there are no other things we are taking into account except mechanical energy. You can have mechanical energy of moving charges. Charges can have some mass, so there will be, half mv square, for instance, kinetic energy, etc. That is assumed in there. Other question is, how can the medium be anisotropic and isotropic? Anisotropic for E and isotropic for B? Well, the reason is that magnetic dipole moments and electric dipole moments, they arise from different physical effects. Remember, magnetic dipole moments arise from motion of charges around closed loops, and electric dipole moments, they arise from separation of centers of charges. Okay, so these are two different physical effects, and there can be situations in which their relative magnitudes are very different, and there can be situations
Dr. Sanjay, did you ask something?
No, I didn't ask anything. So there can be situations in which you can one effect can be isotropic for dynamic. One more time, this is some anonymous attendee, and okay, well, I'll have to first finish what we plan to do, and then maybe we can go back to the energy conservation.
Okay, so probably you can continue because attendance is going on. So that's okay. Please continue.
There are lots of lot of questions being asked. I don't think I can address everything. Okay, there's a one question. Okay, let me just. Aparna has asked, how are left circularly polarized and right circularly polarized are eigenstates? Well, I forgot to mention they are eigenstates of the field angular momentum. Note it down. Okay, so there will be an angular momentum for electric field or magnetic field, and so these are the eigenstates. If you do the quantum theory of that, these are the eigen. So EL and ER are the eigenstates of the field angular momentum, and the eigenvalue will be plus h bar or minus h bar, whether the photon angular momentum is clockwise or anti-clockwise. Well, there's a question about whether the interchange of K and L due to commutative property. Well, yes, linked to that, but the main important point is whenever you have indices which are summed over, you can interchange them in the equation. So that summing over could be arising from different sources, so it doesn't always have to be the dot. Okay. All right, so these are some of the questions. I'm sorry that I couldn't answer all of them. Maybe let's see how much time the second session takes. If there's a time left, we can go back to some of these questions again.
Dr. Sanjay, we also do the following. We will copy the questions from here, and we pass on to the speaker through email. And
okay, then the later
the ones which require very basic ones, you can answer few of them. Yeah.
Okay.
Thank you.
So
Thank you.
those we can do later. All right. So let's. Is my screen visible?
Yes, it is visible.
Okay. All right. So,
And the pointer, I guess, is also visible. So let's go back to our presentation. I will stop my video so that there's a less band requirement. So we got to the result that permittivity tensor is symmetric. Instead of 9 independent components, it has only 6 independent components. All right, there's a second constraint also, and that second constraint arises because the electric field energy density is positive quantity. And that leads to something like this. So what you are saying is a positive quantity is the following. This is expression for the electric field energy density E dot D, and 1/2 factor here. And you write down the expression for D here. Okay. Now here I have written down X and Y components as, you know, X is 1, 1, Y is 2, etc. I'm writing it because we're getting down to something, you know, directly related to geometry. Okay. So E dot D, it's again dot product, no free index. So you have summed over all the coefficients. All right, so these are the terms here. And we have used one fact. Actually, there should have been 9 terms. Okay, because this will have 3 terms, this will have 3 terms. So you're taking product, there should be 9 terms. But this sum has 6 terms. What you have done is, if one term was, for instance, epsilon yz ey ez, the other term would have been epsilon zy ez ey. Okay. But now we know that permittivity tensor is symmetric, so we have used the fact that epsilon is epsilon yz. Okay. That's why we have added those 3 terms to 3 others, so you will end up only with 6 terms. Okay. So this is the constraint here, that this sum of Ex, Ey, Ez, you know, this is called the quadratic form. You know, you have square of the 2 quantities, Ex and Ey, and then their products. Okay. Has to be a positive definite. It has to be some positive quantity. It is just not some any value. It's a constant, but a positive constant. Okay. Now, this is an equation of an ellipsoid in space. And this ellipsoid in space, space in the sense of directions, but this is an ellipsoid which is formed by the components of the electric field. So what it is telling you, that these components, they are constrained in a particular way. They cannot take any value. Now what you have done here is, I've just replaced, you know, this is this equation was in terms of components of electric field. Okay, electric field is a vector. What you've done here, we are written down in terms of position vector. And position vector, you know, is the component of position vector are basically x, y, z coordinates. So it becomes an equation which is encountered in geometry, coordinate geometry. Equation between coordinates x, y, and z. This equation represents, if it was just, you know, this is just equal to 0, okay, greater than 0, some constant. So this represents a surface. We have 3 coordinates, one equation linking them. Okay, there's a relationship between 3 variables. You will get an equation of a surface in space. Okay? And this equation happens to be a surface of an ellipsoid. Okay? Ellipsoid is basically, you know, something whose cross-section is ellipse in 3 orthogonal directions. So I have a diagram which I'll try to show you how it looks like. Okay, so this is an ellipsoid. You know, imagine it in 3 dimensions. So you have, you know, going also behind the screen, and this is one ellipse. It looks like a circle, but it's actually, this is also an ellipse. Okay, and this is the 3rd ellipse. So there are 3 orthogonal ellipses. And so wherever, you know, you can move in one direction or the other direction, the surface, if you take the, if you cut the surface, you will get a curve. That curve would remain an ellipse. Okay, so this is an ellipsoid. Okay, and this ellipsoid is represented by an equation like this. You notice that this ellipsoid is tilted with respect to these coordinates. What we can do is, and this ellipsoid has what are called the principal axis. So this is one principal axis, this is another principal axis, and third will be coming out. Okay. So an ellipsoid will have three orthogonal, perpendicular in space, principal axis. What we can do is, if the coordinate axes are not aligned with the principal axis, we get this long equation. Okay. But what we can do is, you can align the coordinates along the principal axis of the coordinates, or principal axis of the ellipsoid. So basically, you tilt your coordinate axis so that the three orthogonal directions are aligned with the principal axis. The third option will be coming out. That's what I'm not shown here. Okay. So you understood the meaning? What you're doing is, you are turning your coordinate system so that the three axes get aligned with the three principal axes of the coordinate, of the ellipsoid. Okay. In the new coordinate system, the equation for the ellipsoid is much simpler. Which means that you do not have any cross terms like epsilon yz, epsilon zx. They go away. Okay. So basically what you're doing is, okay, there's a constraint on ex, ey, ez. Okay. That constraint looks like this in any arbitrary coordinate system. Okay. Now this equation, this constraint defines an ellipsoid. If you change or reorient your coordinate system so that your coordinate axes are now along the principal axis of this ellipsoid, then the same constraint gets simplified. And that constraint equation does not contain the cross terms, epsilon yz, epsilon xz, etc. So in this particular coordinate system, your permittivity tensor has only diagonal components. If there were an off-diagonal term here, that will violate this constraint. And this constraint has to be observed because of energy density being positive. So we get this very interesting result. Since the energy density is constant, the electric field components, they define an ellipsoid. If you orient your coordinate system along that principal axis of the ellipsoid, then in that representation, permittivity tensor does not have any off-diagonal components. Now, in principle, if you are in this coordinate system, you can go back. You can do a coordinate transformation. And that coordinate transformation would take a tensor which has only diagonal component to a tensor which will have off-diagonal components also. So that can be done. Okay? But the off-diagonal components are arising only from the coordinate transformation. As far as the properties of this ellipsoid are concerned, they're all contained in these three components. Okay, so we don't need to worry about off-diagonal components. So physically, only these three components are important. Okay, this is coming from the requirement that electric field energy density is positive quantity. It's a very strong, interesting mathematical result, but it has a physical consequence. But while going here to here, remember that we have lost. We have fixed our coordinate system now along the ellipsoid principal axis. Now, this is stating these results, the ideas which are here. So, if the coordinate axes are oriented on the principal axis of the permittivity ellipsoid, then there are only three diagonal components. And then we can write down the relationship between D and E like this. In your earlier notation, it would have been epsilon xx, but doesn't matter. Just suppress one x. Or well, this should have been dy instead of dx. So we have only three independent, physically independent components of the ellipsoid of the permittivity tensor. Now let's get back to physics. This was all mathematics. Okay, we noted that there would be whatever the value of ex, ey, ez are, they are constrained to be in an ellipsoid depending upon the energy density. Okay. that orientation of the ellipsoid in space is fixed with the crystal. Okay, remember, you're talking about anisotropic medium, and typical anisotropic medium would be some crystal. Okay, the anisotropy of the crystal will determine the orientation of that ellipsoid. So what you have done is, through some measure, forget how we find it, we figure out the principal axis of that ellipsoid and orient our coordinate axis along those ellipsoid axes. That's what you have done. And then if you write down the equation for expression for vector E and vector D in that coordinate system, which is oriented along the ellipsoid principal axis, you will get this set of simplified equations. Okay? And these then these three values are called the principal dielectric constants. Okay. So keep in mind, I again want to emphasize, principal dielectric constants, they make sense only when your coordinate system is along the principal axis of the ellipsoid. It's not a very general result. The general result would be a symmetric permittivity tensor with 6 components. Now in the remaining time, we quickly discuss crystal classification. It depends, depending upon the value of the three principal dielectric constants, okay, what's the relationship between the three? With the three, you can classify crystals. And that classification we will briefly discuss. So first classification is called the biaxial crystal, in which all the three principal dielectric constants are different from each other. Okay. And if you're talking about the propagation of light, then one can talk about refractive index, which determines the speed of light in that medium. Okay. And Maxwell's equations tell you that the speed of refractive index will be square root of, the ratio of the dielectric constant in the medium to the dielectric constant of vacuum. So we get this result. Okay. And since, epsilon x, epsilon z are different, in principle, you get three different refractive indices for biaxial crystals. Now, those of you who have done, solid state physics, you would know that, depending upon the basic cell, its properties, you can classify crystals in different classes. So there are crystals like triclinic, monoclinic, orthorhombic. All these crystals are biaxial crystals, and for them, the three principal dielectric constants are different. Okay. Well, the next classification would be that two of them are same and the third is different. So Ex and Ey are equal, and Ez, the third one, is different from the other two. Okay. These crystals are called the uniaxial crystals. And well, since this one particular direction in the crystal is different from the other two, we give it a special name. We call it optic axis of the crystal. And tomorrow we'll discuss more about, optic axis of one particular crystal, namely calcite. So, but you understand, there'll be one direction, principal dielectric constant along that will be different from the other two, and that direction we call as optic axis. Here we have, two different refractive indices, one corresponding to x and y, other corresponding to z direction, because epsilon are different. And we give them the name, ordinary and extraordinary. So O, this is not zero, it is O, ordinary. This is E for extraordinary. I think it's a very, very uninspiring name. I wish people would have found some other name, but nevertheless, this is now convention. So you have two different refractive indices. Okay. And tomorrow we'll spend time, discussing how these, what effect do these NO and NE have on the propagation of light in uniaxial crystals. So this is, and there are a number of crystals which are uniaxial. So trigonal, tetragonal, hexagonal crystals are uniaxial. And these are some of the very common examples of uniaxial crystals which are readily available. Quartz, calcite, very cheap, and lithium chloride. There's a host of other, uniaxial crystals. Some are naturally occurring, some have been created artificially. They all have this property of having two different refractive indices. The third obviously is simple, that, all the three are same. That constitutes an isotropic crystal, and cubic crystal are isotropic crystals. So this is a brief introduction to how, depending upon the principal dielectric constants, one can think of three different classes of crystals, okay? And the propagation of E and M waves in these crystals then is very different from each other. Okay? So this is basically what I intended to discuss today. And let me see how much time we have. Well, we have roughly half an hour. So I guess if not all the time, maybe we can take some questions in the remaining time. Okay. Some of these questions, I have already touched upon. Some we'll discuss later. So let's then go to. Okay, there was one question about the Poynting vector and energy conservation, etc. In fact, there are 2 or 3 questions about that. Is the Poynting Varalakshmi is asking, is the Poynting vector gives the energy flow per unit area per unit time to a cross-sectional area along the direction of propagation of wave? Okay. Yes. Okay. In fact, there's a subtle point along when you say propagation of wave, and in uniaxial crystal, the propagation of wave and the propagation of energy are not in the same direction. Okay. We'll touch upon that later. But because there was a question about the energy conservation, so I think. But let me just go for other questions also. Okay, what is the physical significance of permittivity tensor being symmetric? Aditi is asking that. Well, physical significance is in some sense, an ambiguous concept. Physical significance in this context, the one which you are discussing, is basically that if it was not symmetric, then the energy would not be conserved. Reverse it. Since we know that energy of electromagnetic field has to be conserved, then obviously that forces the permittivity tensor to be symmetric. Okay? I think that's how I will put it. I will take that also to be a physical significance. Eigenstates I will answered. Okay, there's a question about electric field and magnetic field. So the concept of polarization we basically discuss only with reference to electric field. Why not magnetic field? This is a question posed by Sudarshan. Well, it is you can as well work with magnetic field. Doesn't matter. Okay. Maxwell's equations also tell you that E and B fields are always orthogonal. Okay. So since they are perpendicular, and in harmonic oscillations, they are all oscillating together. Okay. If you go back to these diagrams, you see A and B are perpendicular, but they're oscillating together. When one is maximum, other is also maximum. When one goes to 0, other also goes to 0. So we could have done this discussion also using electric field. But when you get down to actually looking at anisotropic properties and polarization, it turns out that the electric field effects are much stronger. The Coulomb force law is much stronger. Okay, the coefficient there is much stronger. So magnetic effects are generally much weaker than the electrical effects, unless currents are extremely high. Okay. And at least on Earth circumstances, the currents are not so high. So magnetic field effects are much weaker. They're more difficult to observe. That's why the discussion conventionally has dealt with electric field mostly. But otherwise, it could have been done with magnetic field also. Well, there's a question about gravitational force also, but that's very weak, so we can neglect it at the moment. And at least here, we don't have to worry. So there is a matrix formulation for optics. Yes, there's a matrix formulation, and for different problems in optics, There are different matrix formulations. There's a matrix formulation for propagation of light through optical systems like lenses, for instance. Okay. There are matrix formulations for dealing with polarization. So we can represent polarization states in terms of matrices, and whatever polarization devices you're aware of, for instance, quarter wave plate, half wave plate, etc. All of them can be represented by matrices. So yes, there is HACT has a matrix representation, and in case you're interested, and it gives it in a very, very nice introductory way, so you can have a look at that. There is a question about why we interchanged the indices on the permittivity tensors. See, it was not the permittivity tensor. We looked at the property of the equation, and that property was that both the indices were summed over. So whenever the indices were summed over, irrespective of what tensor it is, okay, you can interchange. So that was the property of the equation, not the permittivity tensor per se. Of course, from that, then we derived another property of the permittivity tensor that came later. Another question about permittivity tensor. See, tensors are physical objects because they appear in physical things. Okay? Now, they are abstract. They are, more difficult to visualize. Okay? There are certain tensors which are more directly physical in the sense that they are there by themselves, like gravitation field in Einstein's general theory of relativity. Okay, that many of you would not have dealt with. Most of the tensors which you have dealt with, whether it's the stress tensor or whether it's, this permittivity tensor, these tensors, they appear in relationship between two quantities. In particularly, relationship between two vector quantities. Okay? Now, I will advise you to think about, when you think about physical things, see, there are two ways to look at it. Our normal way of looking at physical things is to look at them in isolation, in separation from everything else. Okay? So you can have a mass, that's a physical thing. A charge, a physical thing. Irrespective of what is around or what is the relationship of that mass with something else, doesn't matter. Okay? That mass is something which is contained in itself. It's a property of a thing. Similarly, charge is a thing. In our normal way of thinking, we are more comfortable with physical things like that. But I would advise you to start thinking of physical things also as relationships. Okay? They are physical things, they are physical relationships. So the tensors which you are dealing with, look at them as physical in the way of relationships. So relationship between two vectors, electric displacement and electric field, okay, in a given medium is represented through or via the permittivity tensor. So if you start looking at relationships also as physical things, as physical relations, then I guess you will be more comfortable in appreciating that permittivity tensor is also a physical thing. So look at it as a relationship. That's what advice I can give you. Otherwise, if I have to say, okay, what thing it is, that is difficult to say. Okay, I've answered that earlier. Sumohan asked, sir, only as the permittivity tensor is symmetric, the interchange was possible. No, I told already that interchange was possible because of the character of the equation. In fact, symmetric nature of the tensor was derived later. So we didn't assume the symmetric property earlier to do the interchange. Okay, in what sense the electrically anisotropic medium differ from isotropic system? Well, I think all we can say is that without going into very details, anisotropic systems would have different properties in different directions. And we have seen that, well, we are not proven it, but we're just telling is if you have crystals, then it's possible that, then it is possible, depending on what kind of crystal it is, that its dielectric properties, propagation of speed of light, polarization state of the light, etc., will be different in different directions. So that will make it anisotropic. Okay? And isotropic means that it is same in all directions. So, okay, what is the origin of random polarization? Okay, see, when you talk about the random polarization, Akshita is asking, see, the light actually, if you think about the origin of the light, it is made up of photons, and all the photons, at least the visible light photons, they basically arise from transitions between electronic orbits inside some atom or molecule, mostly atoms, okay? Because when because the energy levels of electronic orbits, their energy differences correspond to the energy of the visible photons, okay? So there is a mechanism through which these optical photons are created, and that mechanism is the electronic transitions inside atoms, okay? So the light which you receive, that is effectively coming from a large number of superposition of large number of such photons. And each of these photon has been separately emitted by a different atom. Okay? And since the transitions, electronic transitions between different atoms are random, okay, you're not dealing with laser phenomena, you're dealing with natural phenomena in which these transitions would be random. That's why these photons, different photons, they will come out with different phases, different polarization, etc., etc. Okay? And when you combine all of them, the light will become randomized. Its polarization at a given instant will change randomly from moment to moment. Okay? So that's how one can think of, how the light, the randomly polarized light arises. Okay? In fact, for creating polarized light, you have to have special cases, special equipment as devices. Most of the natural light is unpolarized because of the way it is produced in the electronic orbits. What is electric field energy density? Well, that is the Well, Saurabh Verma is asking a question. Electric field component is also a function of time. So fixing our coordinate system doesn't cancel out cross terms. No, that's the whole beauty. Okay. The time variation could be any variation, but since you can pick any moment, or you can put that moment t to be 0, that doesn't matter. So for any time, if you have proven some result for a given time, it will hold true for all the time. So it is not, the time here doesn't play a role here. Well, there's a question about ordinary and extraordinary. We'll come to that later. Tomorrow we'll do that. Raghvendra had asked that. Well, Marilina is asking, if the light, how do you find out if the light is circularly polarized or spherically polarized? I mean, there's no spherical polarization. Yes, there are circular and elliptically polarization. Tomorrow, if you have time, you might discuss, there are specific ways in which you can figure out the polarization property of a light. Okay? You can use certain instruments to do that. And we might that tomorrow if you have enough time. The principal axis, okay, there's a very interesting question here. Harsh has asked, does it mean that, does the principal axis and principal value means that there exists a direction in which electric field is applied, the polarization vector will be in the same direction? Yes, if you apply the field along one principal axis, not along others, okay, then the induced polarization would be parallel to it. Yes. But that's the case, see, okay, but it's only when you have arbitrary directions that, E is not parallel to, E and P are not parallel. The more general case is not being parallel, but you can have special cases in which they are parallel. No, see, we discussed that, that whether Arya Gori is asking, we took the electric field energy density to be a positive constant. Yes, it can, of course, if the electric field is oscillating, it would vary with time. But, at any moment, it's a positive constant. That's what we wanted. And since it varies with time, obviously, The constant would change with time, but that doesn't matter. We are looking at the situation at a given moment. Okay, there's a question about can we apply, the Mridul is asking, can we apply the same concept of easy or difficult direction of polarization to magnetic moments? Yes, we can do that. Okay. There would be certain cases in which magnetization would be easy in one direction than in another direction, depending upon certain properties of the crystals. Okay. All right. Okay, so that I think basically takes care of all the questions which I could think of. What's the time here? How many minutes we have? Well, we have 15 more minutes. So maybe we can go back to the, because there was a question about energy pointing vector and energy density. I hope that I had prepared, more slides according for that in particular. But what is going? Okay, I'm just going back just a minute. I'll go back to the energy conservation thing. Okay, so these are the basic equations which you have to deal with energy conservation in electrodynamics. Okay. This part, I guess, is straightforward. Okay, if you look at just the integral, this is the total energy contained in volume V. Okay? And then we are taking d by dt of that. So how that thing is changing. Okay? Imagine that the total energy in the volume is increasing. All right, suppose it is increasing. So then this d by dt would be a positive quantity, but it comes with an extra negative sign. So the right hand side then would be a negative quantity. Okay, all right. The case is that the total energy inside this volume is increasing. In that case, this right hand side would be a positive quantity. Okay? So obviously, this thing also had to be a positive quantity. Left hand side also had to be a positive quantity. Okay. Now let's look at this left hand side integral. You have, it's a closed surface, remember? And for a closed surface, your A unit vector is outward. Okay. So dA vector, you can think of, I'm just drawing a closed kind of surface with my pointer. Imagine this is a sphere, okay? So the unit vector will be outward at every point. dA would be outward, okay? Okay. What you want is that S dot dA should be positive. Wait a minute. Should be negative, sorry. So it should be negative because d by dt was positive. There's a negative sign here. So what we want is S dot dA to be a negative. Okay. So now you can imagine what should be the average direction of S so that surface integral of S dot dA is negative. S should be going in. Only dA is out. S should be in so that S dot dA is a negative quantity. So when energy inside the volume is increasing, S should be such that it is directed inwards. Okay? And that gives us the physical interpretation of S. The energy is flowing along S. Okay? S is a vector quantity, it is a direction. So energy is flowing along S. And the magnitude of S then is, since you have S dot dA, okay, and the right hand side is the increase in the total amount of energy per unit time. Okay. So S dot dA should give you how much energy is flowing into the volume per unit time, which means S is energy flowing per unit time per unit area, because S dot dA should give you total energy per unit time. Okay. So that's how the interpretation of S comes as rate of flow of field energy per unit area. Okay. Now this particular expression of S, it comes from Maxwell's equations, a whole long derivation. We can't go into it. But what I wanted to emphasize is to appreciate the fact that E and V don't have to change with time for flow of energy to take place. You could have constant E, constant V. As long as E cross B is non-zero, there would be a flow of energy, of electromagnetic field energy. Very interesting result. It appears counterintuitive. Fields are not changing with time, but energy associated with them is flowing. Okay, all right. And those of you, if you have looked at, the book by Griffiths, he discusses a very interesting example. Book on electrodynamics by Griffiths. He discusses a very interesting example. Unfortunately, I have not prepared a slide for that. But let me try to, show you. Maybe I can just use my hands or, Okay. Wait a minute. Can I share a blackboard or something? Let me see. There used to be an option for using a blackboard in Zoom. I don't see it here. So I can't draw diagrams right now. But let me just try to move my hands to
So I think some network issue from at Dr. at Dr. Sanjay's end. He has just exited, right? Okay. So Dr. Partha Goswami is already along with us for the next session. And I request Dr. Partha Goswami to kindly show his video. Yes, yes. So he's there with her. Good evening, sir.
Good evening.
Good evening, sir. Good evening. And I request Dr. Divya to kindly share her screen for a moment. So we had a very nice session just now.
Yeah,
with Dr.
joined
Sanjay.
in.
Yeah, yes, a very nice session regarding polarization. And so he will continue with us tomorrow again for his session on polarization. And so we would now start your lecture. Yes, Dr. Divya, we start with Dr. Partho's lecture now.
Yes, sir. I welcome you, sir. Very good evening, and it is
Thank
our
you.
pleasure to have you here. So, students are waiting for your lecture. So, we shall start now.
Yeah.
Yeah, so for the students who have joined for the first time today, although they are very rare ones, mostly we are having persistent learners. So today sir is going to speak about motion in EM field. And Dr. Partha Goswami, he's an MSc, MPhil and PhD from University of Delhi. He's presently working as an associate professor in physics in Deshbandhu College. He has done his graduation with first position from St. Xavier's College, Ranchi. He has been teaching mathematical physics to BSc Physics honors and students for the past 30 years. His area of specialization is condensed matter physics theory, and he has 26 research papers to his credit, mostly under sole authorship, published in prestigious journals of physics. And apart from that, I've seen that sir is a very, very passionate person as far as education and pedagogy is concerned. And amongst the group of teachers, we are eagerly looking forward to his small paragraphs almost each day regarding either pedagogy or something related to condensed matter physics and all. And he is a source of inspiration to a large body of teachers, that as one progresses in life, one must keep on having various interests and one must always be a learner. So, welcome you, sir, once again to our series of NASI for learning physics with conceptual and problem based approach. And we are looking forward to your continuation of classical dynamics with us. So, I request now the slides of Dr. Partha Goswami to be displayed. Ms. Varsha.
Yeah, good evening, everybody. May I begin now, ma'am?
Yes, sir, you will be able to see the slides. Just one
Yeah.
second, and then you can start. We just, Miss Varsha, kindly share your screen. Yes, please use.
Yeah.
Please use.
Yeah, it is visible.
Yes.
Okay. Good evening, everybody. My thanks goes to Dr. Punita for very, very kind words. Actually, we are all learning. So there is no special credit goes to me just because I am on learning curve. Anyway, so our topic of discussion is the motion of a charged particle in electromagnetic field, or maybe only in electric field or only in magnetic field. Now, motion of charged particle in the simultaneous presence of both electric and magnetic fields has variety of manifestations, ranging from straight line motion to cycloid and to other complex motion. Both electric and magnetic fields, they impart acceleration to charged particle. Electric field, of course, brings about change in magnitude. Magnetic field brings about change in direction. But for the reason that magnetic force is a cross product of velocity and the magnetic field. Uh, now, uh, you see, magnetic force being cross product will always be normal to the velocity of the charged particle and will tend to move the charged particle in a circular trajectory. On the other hand, electric force is either, depending on the nature of charge, either along the direction of the velocity or it is creating retardation. So electric force would be capable of bringing about change in both direction and magnitude if electric field, of course, is at right angles to the motion of the particle. There would be also change in direction, and so depending on the velocity and electric vector angle, the path of the path that the charged particle follows under action of electric field will be a parabolic path. So there is a great importance of this. I'm speaking by way of introduction. I have not really written them down in my slide. Um, uh, so I believe such things, whatever I'm saying, as mostly known to everybody. Now, we generally refer to crossed fields. Crossed fields means electric and magnetic fields are at right angles. Let me tell you that crossed fields act as velocity filter. In what way? Suppose I have electric field applied to the charged particle. That would exert an electric force Q times E. Now I apply magnetic field perpendicular to the direction of motion of the particle, which will, because magnetic force is given by Q times B cross B. So the force due to magnetic field with appropriate direction of magnetic field chosen could counter the direction of electric force. So in that event, the charged particle will not experience any force. So if I have such a situation, obviously it means Q times E, which is electric force, equal Q times B, which is magnetic force. So V becomes E by B. That means those particles which have velocity equal electric field magnitude upon magnetic field magnitude will pass through the electric field and electromagnetic field, now crossed one, undeviated. On the other hand, those with velocity different from E by B will get deviated either in the upward or the downward direction. So definitely, if we put now suppose a slit in the path of the charged particle, then we would find that through this slit, those particles would come out whose velocities are precisely equal E by B. That means you had a beam of particles, let's say, with a spectrum of velocities. You have been able to filter out those particles which have velocity equal only E by B. So a cross field, as I said, acts as velocity filter. These crossed fields also have importance in determining specific charge of electron in cyclotron and so on. So before we proceed, one thing we must understand that our charged particle have masses, say a proton of order 10 to the power minus 28 kg, an electron even less, 10 to the power minus 31 kg. So even a small electric or magnetic force is capable to generate very high acceleration of the order, let's say 10 to the power 12 meters per second or more. So under proper setup, these charged particles can attain velocity compared to speed of light, and then they enter into the relativistic domain. Our discussion, however, would remain confined to the non-relativistic domain only, wherein particles have speed much less than the speed of light. So with this, now let's refer to the first slide. In the first slide, which is projected on the screen, I have written down we assumed that our fields, electric and magnetic fields, which together we call as electromagnetic fields, they are spatially and temporally uniform. That means neither from point to point in space, the fields are varying, and not even with respect to time. Temporally means pertaining to time. So equation of motion, because we are in non-relativistic domain, equation of motion will be given by usual Newton's law. So mass times acceleration dV/dt is this Lorentz force, which we call E times E plus V cross B. Now, I may split the field, electric field, as say parallel component, the component parallel to the magnetic field. For this component, the equation of motion reduces to dV parallel dt equal E by M E parallel. So a component of electric field parallel to magnetic field will give me definitely an acceleration or retardation depending on in which direction it is there. So now, in fact, we when we talk of assembly of charged particles, we mostly talk of plasma. Like plasma comprises of uh, ions and the electrons, and so plasma in near equilibrium have generally either very small or vanishing component of E parallel. Therefore, acceleration or deceleration expected would also be for plasma rather insignificant. With this, we go to the second slide, wherein we consider the perpendicular component of the velocity, and Newton's law application in previous equation gives me mass times change in perpendicular rate of change of perpendicular velocity component perpendicular to the direction of the field. Magnetic field, to be precise, is equal Q E perpendicular. Electric field I have split it into parallel and perpendicular component. So E perpendicular plus B perpendicular cross B. So we make this transformation, make a transformation now into a reference frame where the drift velocity VE is such that V is V plus VC. The drifting frame, in the drifting frame, the velocity VC is actually the velocity of cyclotron motion, and VE is perpendicular to B. Equation, if V is perpendicular to B, equation earlier I quoted, that is md V perpendicular dt Q E perpendicular plus V perpendicular cross B, this reduces to m dvc dt equal Q E perpendicular plus V E cross B plus Q times VC cross B. So one sees that the BE being perpendicular to B has no B being perpendicular to B, I would have two terms as far as the magnetic force is concerned. One is Q times V cross B, and another is Q times VC cross B. Now we go to, I think these equations which I have written down, two equations in the second slide, are very easy to understand. There is, what I simply have done is applied Newton's law. Mass times acceleration is equal the force acting, and forces are forces due to electric and magnetic field, which are, I suppose, is well known. Of course, I have, as I stated, made an additional transformation to a reference frame where V is, where velocity of drift is such that V is V plus VC. Point, I'm sorry, I forgot to mention, I should have emphasized it. The point is, the VE is a steady, assumingly a steady drift velocity. Therefore, in the final equation in the second slide, m dvc dt, I don't have the component of VE, because V being constant, derivative with respect to time would vanish. So how we go from previous equation to this one is pretty clear. It should be pretty clear to everybody, I think so. Now we go to the third slide, please. Once we go to third slide, we can see that, is it third slide? Oh yeah, it is third. Hello, is it third slide? Hello?
Yes, sir, it is third slide only.
It is third slide only. Okay. So in an effort to solve for V, the drift velocity, E perpendicular plus V cross B equals 0. And then we use a well-known identity in vector algebra. A cross B cross C is B times C dot A minus A times C dot B. And we write E cross B, magnetic field, as minus V cross B, which ultimately comes to how much? VEB square minus B times VB dot B. So the if I set this E perpendicular plus B cross as 0 and use this expression for E perpendicular cross B, I land up with the expression for steady drift velocity V equal E perpendicular cross B whole divided by B square. I think it is clear to everybody how have we come at this expression for steady drift velocity. Is it clear? Is it clear to everybody? Hello? Hello?
Students, please reply. In the question answer box, you can write yes or no.
Hello? Is it clear?
Yes, sir.
It is clear.
Yes.
Yes, sir, it is clear. The students are writing in the chat box. It is clear to everyone.
Achha, it is clear. Okay, yeah, I can see that. Okay, so we have okay. Now we have thus an expression for the drift velocity v, which is E perpendicular cross B divided by B square, magnitude of square of the magnitude of the magnetic field. So this drift is termed as E cross B drift by plasma physicists. We go to the fourth slide. In plasma, the fourth slide, in plasma, we have, as I said, ions and electrons. Ions, of course, are heavier. They mostly, so this is ionized state of matter, fourth state of matter, as we all know. Drift is identical for all plasma species. Can be entirely eliminated by going to a new inertial frame in which E perpendicular is 0. Because our expression, if I look at the title strip, BE is E perpendicular cross B whole divided by B square. This is our E cross B drift velocity. So if I go over to a new inertial frame in which E perpendicular is 0, we are eliminating the drift velocity V entirely. So this frame would move with velocity v with respect to the old frame and can be regarded as rest frame of the plasma. This inertial frame could be regarded as the rest frame of the plasma. So now that we have Newton's law application giving me an acceleration, which ultimately upon integration leads to integration once, leads to velocity, and velocity upon integration leads to the position. So we have the expression for position vector below fourth slide, RT, R as a function of time, as capital RT and rho t. Capital RT is, of course, initial velocity in the parallel direction to the magnetic field T, because there is an acceleration. So you apply your well-known formula V S distance as half AD square known from your school days. So you get V0 parallel T equal E by M times E parallel, which is acceleration, and half T square, a unit vector B, of course. This unit vector small b is capital B vector, that is magnetic field vector, divided by its magnitude. Capital B vector, that is magnetic field vector, divided by its magnitude. This is naturally then this unit vector B in the direction of the magnetic field. And this is, and here we have added the drift velocity as well, which we talked about, Vt. Well, this expression for RT is very easy topic, further explanation. Therefore, I may fifth slide to give you the expression for rho. Expression for rho involves, in fact, uh, as you see, your magnetic force is Q times V cross B. And V cross B is a vector which could be written out, of course, in usual form, determinant of ijk, Vx, Vy, Vz, and magnetic field may be assumed in a certain direction, let's say z direction 0, 0, B. So we shall get mass times velocity component variation along x direction with time equal QB, Q being charge, B being magnetic field, and with that Vy multiplied. On the other hand, M times Q dV by dt will give me minus QB Vx. So I shall have a what you call coupled differential equation system. Coupled equations are usually decoupled at higher order. So when we decouple and take the second order derivative, we get usual harmonic oscillator equations in x and y direction, which is what I have written down, rho t equal minus rho E1, a unit vector, of course, cosine omega t omega 0 E2 unit vector sine omega t omega 0. This is coming from the fact which just now I have stated, that the magnetic field, when dealt with differential equations obtained, they are coupled equations. You uncouple them in higher order, in second order, which leads you to usual differential equation for harmonic oscillation. And this is why you have obtained two terms here in perpendicular direction two harmonic oscillations, which of course two perpendicular harmonic oscillations combined together give a circular motion. So we had written down the trajectory of the particle in this case together with displacement RT, and together with the fact rho t is representing a circular motion, will be a spiral, and spiral meaning helical, like a spring. So the gyro center of the spiral, termed as the guiding center by plasma physicists, drifts across the magnetic field, of course, with velocity VE, which we have shown in the previous slide, and also accelerates at a rate determined by parallel component of the electric field E parallel. In the fourth slide, we have seen those expressions. And omega here is EB by M. It's cyclotron frequency. This is also called gyro frequency, and rho is called gyro radius. E1, E2, B, they form a right-handed mutually orthogonal set of basis vectors. Gamma naught here is the initial gyro phase of the particle. So motion is a consists of gyration around the magnetic field with a frequency omega. Superimposed on it is a steady drift at velocity VE. Now let me ask my explanation, which was to better part verbal. I have written, I have not written much of mathematics in the slide. Is the explanation verbal only? And whatever is written in the slides, is that clear to everybody? Hello, is that clear?
Yes, sir, they are saying it is clear.
It is clear, very good. Okay. Now, in the sixth slide, if you go, please, then we find that we have, from our previous discussion, we have shown, now we are in a position to put it in pictorial, give a pictorial depiction. We have XYZ axes. Along Z axis, as I said, we have the magnetic field, and electric field, of course, is in XZ plane at a certain angle to magnetic field. So, well, the direction of electric field here, if that angle between E and B is 90, the electric and magnetic field will be said to be orthogonal. So when we immerse the particle, charged particle, in orthogonal electric magnetic field, electrons and ions, we show they drift in the same direction and with the same velocity. Why so? Why same direction and same velocity? I put it as a poser for students to find themselves out. Why the ion and the electron both, when immersed in orthogonal electromagnetic fields, will be drifting in the same direction. Apparently, they should not, because ions have positive charge and the electrons have negative charge, and also with the same velocity, which also apparently seems not feasible, reason than electron. So here we have assumed magnetic field being in the z direction away from the plane of the figure, and electric field is, as I said, making an angle of 90 degree, so along x-axis. I want students themselves to figure it out. If they don't, if they are not able to, they can always get back to me through Madam Dr. Punita. But something should, some exercise they need to do. So I thought I leave this as an exercise for them to figure out. Now we go to 8th slide and summarize here. I have simply summarized what I have obtained so far in the 8th slide. The gyro radius is also called Larmor radius. So Larmor radius or gyro radius of a charged particle gyrating in a magnetic field, rho. Well, this rho is Vt upon sigma that, and omega, sorry, omega is QB by M. So it becomes MV divided by QB, and MV divided by QB could easily be obtained by what a student knows by equating the magnetic force QVB with, which is providing for to particle the centripetal force to move in a circular path. That is, you are equating QVB with MV square by R, or rho rather. So rho ultimately leading you to MV by QB. I believe how you have obtained this Larmor radius or gyro radius is too easy to understand. We simply have equated or simply have invoked the fact that the magnetic force is providing the necessary centripetal force to describe a circular orbit. And the frequency omega, or angular frequency, rather, this is angular frequency, not real frequency. The real frequency, of course, will be omega by 2 pi. So angular frequency is EV by M, which also is clear from the equation of motion which I have explained. And this is called gyro frequency associated with the gyration. When ions and electron temperatures are comparable, the electron gyro radius will be distinctly smaller than the ion gyro radius. That is obvious from the fact that you have rho equal mv upon qb. Electron mass is much too smaller than the ionic mass. So electron gyro radius will definitely be smaller than the ionic gyro radius, which is what in fact I have shown. Please go to the 6th slide. Please go to the 6th slide, which is what I have shown as well. For ion, the gyro radius is larger. For electron, gyro radius is smaller. Now with this we go to the 9th slide. I have just put in a problem. Suppose we have a velocity, when velocity is perpendicular to magnetic field, and we are considering only magnetic field, and we have a charged particle. We all know motion will be circular. Why? Because velocity is perpendicular to magnetic field. So magnetic force will be QVB, and that just now I have said is providing me the necessary centripetal force for movement in circular path. So centripetal force being mv square by r, and so we have motion in uh, perpendicular magnetic field, perpendicular to velocity, the trajectory as circular with radius as mv by qb. I had already mentioned this. Now, if the velocity is not perpendicular to magnetic field, and we have only, at the moment, we are considering magnetic field only, then what will happen? I have from Newton's law m dv dt equal q times b cross b. Suppose magnetic field is along z direction. So b cross b can, this is a cross product of vectors where you are familiar how to write it out. Write it out in the form of a determinant I, j, k, where these are unit vectors along x, y, and z axes. And V suppose has components Vx, Vy, and Vz, and magnetic field has is along z direction. So the components are 0, 0, and B only. B being the magnetic field along z direction. So substituting these in the determinant ijk, vx, vy, vz, 0, 0, b, and working it out, I get from Newton's law, m dv dx is qv by m dv dy dt minus qb vx, and m dv z dt equals 0. So from the third equation, we find that vz is constant, and if vz is constant, obviously the z coordinates will correspond to a straight line, z equal vzt plus z0. Z0 is of course integration constant. Now I already have mentioned that the two equations, first two equations, they are as one can see, they are a coupled equation. With derivative of Vx, you have variable Vy, and with derivative of Vy, you have a variable Vx. So how to solve this coupled differential equation? I already have mentioned that solution to the coupled differential equation is possible by decoupling them to higher order. In higher order, if I decouple, if I take higher order, meaning go over to second order, I get d2 vx dd square as qb upon m multiplied
Hello, sir, can you hear me?
I
Hello?
think there is a network problem with sir's network problem.
Dr. Partha, if you can hear me, can you please close your video? Then you will require, has he been exited? Hello?
Yes, ma'am.
Hello?
Hello.
Your voice is not audible.
Ma'am, I think there is a network issue, because of that sir also left.
Okay, so just 1 minute. I think just give me 1 minute and I call him up immediately, right?
Yes, ma'am.
Meanwhile, students, if you have any real problem, then you write it on chat. Otherwise, not. There's an announcement that you You must be very attentive towards your email, because there'll be more updates coming on your way through your email. And very soon we'll be filtering 500 persistent learners to whom only the Zoom link will be sent. So please do not complain later on by writing n number of mails to me. Therefore, I request you to please be attentive on email and on your attention towards your attendance link, right? Meanwhile, since there is already a break, why don't you just give the second attendance link to the students so that they can.
Okay, okay, ma'am.
Sir is back. Sir is back. Sir, what was
Yeah,
network?
there was some glitch. I don't know what had happened.
Okay.
I got disconnected.
Okay, doesn't matter, sir. This happens. That's a parameter in
Yeah,
our equation of learning.
yeah, sure. So
Please
shall I continue?
yeah.
Okay.
Yes, sir.
So
We have 20
we
minutes
are.
more, please.
I have ninth slide, which is being shown. In the ninth slide, I have two equations. Third equation has given me Vz constant and Z as a Vzt plus Z0 equation of straight line. So that is settled. But the other two equations, the first two equations, they are coupled, they get decoupled in higher order. And so we go to the second order, we get, as I mentioned, we get harmonic oscillator equation shown in the previous slide. So that there would be harmonic oscillator motion or harmonic oscillation along x and y direction in the two perpendicular directions, which will which will give rise to a circular path. So therefore, if I now take the stock of the situation, I have a circular path in the xy plane, and z coordinate of the particle is evolving in time in a linear manner. And such a situation is actually, this refers to the kind of path which is called helical. So therefore, when we have velocity not perpendicular, we are still on ninth slide.
Okay, sir.
Sorry, we are still on ninth slide. So when we in 11th slide you are showing. Sorry, you go to the 11th slide, please. Go to the 11th slide. Yeah. So I have shown this helical motion. You have in xy plane circular motion, together with that along z direction we have the evolution of z coordinate with time in a linear manner. This corresponds to a helix. So when velocity of a charged particle is not perpendicular to magnetic field, and you have only magnetic field, motion of the particle will be helical. Now, after ninth slide, we come to the 10th one, where I have in the 10th slide explained, I have taken a negatively charged particle which moves in the plane of the page. The page meaning here the monitor plane. Uh, so in the plane of the monitor plane, in a region where magnetic field is perpendicular into this monitor plane, and they are represented by small circle with crosses like the tails of arrows, and magnetic force is perpendicular to the velocity I have shown it. So velocity changes its direction but not magnitude, and that results in a uniform circular motion. With this we go to the 11th slide, which I already have explained. There is nothing to explain more on this slide. Now we go to the 12th slide. In the 12th slide, I have shown trails of bubbles which are produced by high energy charged particles moving through superheated liquid hydrogen. Hello, I am audible? Hello, am I audible?
Yes, sir.
Okay. So this is 12th slide is being shown, where we have shown trails of bubbles which are produced by high energy charged particle moving through superheated liquid hydrogen. Artist's rendition of a bubble chamber. This is an artist rendition of a bubble chamber. And we have, in fact, I'm sorry, I got again disconnected. I don't know why.
Sir, it may be the network problem. You are not audible again.
There must be some. Okay, let me again try to show him. Yeah. Am I now visible?
Yes,
Or
sir.
visible and audible? Yeah.
Yes, sir.
So we have shown the artist rendition of bubble chamber, wherein one can see a lot of these circular paths that the in a strong magnetic field particle moving in such curved path charged particles, and the radius of the path can be used to find the mass, charge, energy of the particle mass. For example, we know the mass spectrograph, etc. Their principle, the radius could be. Let me ask you one question to everybody. In fact, this question was asked to me long time back by one philosophy professor. Philosophy is, of course, related to physics. So he was curious to know that you say, you people, meaning physics people, you keep uttering that, okay, you have uranium 235 nucleus. You have as many as 235 nucleons, wherein 92 protons are there, and rest of the 235 minus 92 neutrons. Well, nucleus, he said, as I understand, is an incredibly small volume. It has an abysmally small volume with linear dimension as much as 1 Fermi, which is 10 to the power minus 15 meter. And uncertainty principle holds out there, definitely. Uncertainty principle holds anyway in any volume whose linear dimension is of the order of few nanometers or 10 hundreds of nanometers, but not micron. From micron onwards, you have microscopic regime. Anyway, so uncertainty principle holds. Particles are indistinguishable. You claim that neutron, protons are fermions. They are indistinguishable. Question is, how did you count that there are 92 protons and 235 minus 92 neutrons? Say, in case of uranium, 235, 92. How is this counting done? Uncertainty principle prohibits you to, we all know that if we measure momentum very precisely, position becomes too much uncertain, and all such things we all know. So, and particles are indistinguishable. So how have you counted this? That was his question. And I put now this question to my students. Can anyone tell me how do these countings done? Is my question clear to everybody? Hello? Hello?
Yes, sir, we are listening. The students are answering on the chat box.
Yeah.
Students, you are please enable chat, Zoom chat, and please allow students to answer. Yes, sir, it is clear to everybody.
The question is clear. So, what is the answer to the question? That is the most important thing. Because in micro world of nucleus, counting is not possible, but we do count and we do say that uranium 23592, for example, has so many protons, so many neutrons. Someone has made the counting definitely. So how is this counting done? This has relevance to what we have discussed just now.
Sir, there are many answers. Somebody says they can be measured by either writing too fast, 1 minute. So one person says by studying the motion of particle in uniform fields. The other one says through
Exactly. That
EM
is what it
fields.
is. Yeah, sure. That is what it
Analyzing the
is.
paths
Whoever has,
conditions.
yeah, exactly. I have shown this artist in the 12th slide, artist rendition of the paths of the particles. So suppose I need to know for a given nucleus how many nucleons are present out there, how many protons. Neutrons, of course, are neutral particle. They will not get affected by electromagnetic field. So how many protons? So in that case, the paths in the bubble chamber which I had depicted would allow me to make counting. So this diagram actually is a projection of what is happening in the micro world. It is the projection of that in macro world. So counting is essentially is a macro world related process, and we get the projection of micro world into macro world like these tracks, and we make counting. So that, I think, that is what the answer I gave to him, and I think it is the most plausible answer. If students have anything else to say, they can, or they can come up with it. Anything else to say?
So one student, Aparna, says deflections of both protons and neutrons are different. And
Neutrons cannot get deflected.
that is,
Neutrons
they are neutral and will not interact in any way with the EM field.
with the EM field, no interaction.
Yes, Gaurav
Neutrons
Datta says,
cannot get deflected.
yes, correct, sir. Gaurav Datta says the uranium nuclei is allowed to undergo through a uniform magnetic field. In doing so, we get the radius of the path, and through that, we can get an idea of the mass using the.
He's gone wrong. Uranium nucleus per se is charge neutral. It is to be smashed up by giving energy, equal its binding energy, so it will throw up all the constituents
I
that
thought
it
that
is
he's
made up
talking
of.
about the charged uranium. He's talking about the uranium nucleus. Nucleus is always neutral.
And uranium nucleus, uranium
Always neutral.
nucleus, of course, is charged, but that will not enable us to make counting. It will give me only a path, a radius of, say, radius of charge as much as 92 E, isn't it?
Yes, sir.
Particles are to be, particles, the constituents are to be, uh, the nucleus has to be fragmented, ruptured, smashed up, constituents obtained. The protons in particular would get affected by field. They will have this kind of track, which circular track, which I have shown. So counting the track, this is of course a very ancient method, but anyway, counting the track, one can get an idea how many protons are there. But what about neutrons? What about neutrons? Neutrons do not get affected by electromagnetic field.
So they have not yet studied interaction of neutrons with matter, and hence probably they cannot answer.
No, electromagnetic field. So this is only a quiz question. Anything they can come up with, maybe very bizarre. Maybe I'm not expecting that. We are simply discussing interaction of charged particle with electromagnetic field. So there we have no novelty, nothing. Everything is well settled. I'm just asking what would cross the mind of students, how to do the bookkeeping of neutrons. It's just a question.
So somebody writes
What do
mass
they think?
spectrograph. Somebody writes, can it be due to the interaction of spins of neutrons with magnetic field?
Well, a mass spectrograph is not possible because mass spectrograph once again depends on magnetic field, and neutron will not get affected by spin, or rather angular momentum is a plausible answer which has some meaning. A neutron, though is charge neutral, they do have magnetic
Interaction.
movement. They do have magnetic movement, and that too negative magnetic movement. That too negative magnetic movement. So since they have magnetic movement, so whatever student has said, and of course they have spin. It's neutrons are fermions, so spin magnetic moment also is there. So something could be done with that, but though going over to spin and other things is transcending our limit, where we are going to quantum mechanical domain. We actually want some answer in the remaining in the domain of whatever we have learned. I put this question now in a slightly different way. You see, the principle that I have discussed at this moment also applies to a cyclotron. One has studied probably at 12th level. Therefore, I don't need to really go into the details of a cyclotron. Cyclotron, you see, once again accelerates. This is a particle accelerator. It accelerates charged particles. But supposing I am to accelerate a neutron, how do I go about it? How do I go about it? Anyway, these are questions, and I think we are closing. Our time is going to be up. These are questions which I leave students to figure out. And if they can come up with, after studying a bit, they can come up with some answer, they can respond, or else they can send their query, they send these questions as their queries, they will get the answer. Uh, uh, I think, madam, now I can stop.
Yes, sir. That is really a wonderful, again, follow-up of your classical dynamics series. I request the attendance link to be put into the Zoom webinar chat box right now. So, sir, you will be, what would you be doing tomorrow with us during classical dynamics?
Tomorrow, I would like to mainly discuss, because I have done only Lagrangian approach and the Hamilton's principle. Hamiltonian approach, or getting Hamilton's equation of motion, which are first order differential equation, and how to get uh, a Hamiltonian from a Lagrangian, because these are kind of questions which are generally asked. So for a charged particle, suppose, in fact, I had to stop perforce in the last lecture when I was discussing Lagrangian calculation of a charged particle. So anyway, we can continue with that a bit and finish that off. And with that, I can show how to get Hamiltonian of a charged particle from starting from Lagrangian and Euler-Lagrange equations. So that means, in a nutshell, the Hamiltonian mechanics or Hamiltonian formulation of mechanics will be the central theme of tomorrow's lecture. The student can come prepared.
Yes, yes. So especially the students who have to appear for their final examinations, they must do a thorough revision of
Yeah.
Lagrange's equations, the Hamilton's equations, the Hamiltonian, and so on. Hamilton's principle and application to
The various
yes,
problems.
yes, yes, yes. Because then only if you spend this whole program has been planned in such a way that it allows you the whole day to give some time to the revision of the concepts which are not strong with you. If they might be strong, okay, then you can go ahead. However, if your base is not correct, you have enough time to continue. So we started 1 week almost, we started on Monday, and this is Saturday, and we are continuing with classical dynamics. And now we have just started EMT from yesterday. So in the following week, we will have EMT classes and statistical mechanics classes till 9th August. And classical dynamics will be tomorrow, probably one of the last classes. So
Yeah, it is good.
I request all the students to kindly revise all these concepts so that you can ask appropriate questions, and also make a list of questions which we can forward to sir for any doubt class that you require, if required. However, the time is really short. We had intended to start the program some more than 2.5 weeks ago. Then we would have got a longer time for each subject. But now we have to complete 3 subjects in 2 weeks, and hence time is really not sufficient. However, I'm sure listening to all these lectures, once attention is drawn and focused towards what are the important things for revision and for grasping, and also for any kind of entrance exam, these are the most important things. And sir has actually given a very detailed concept-wise progression into the subject and understanding also. So thank you very much, sir. And if you feel like sharing any more problems or numericals with the students, you shall be kindly sending them on to our email ID, and we shall pass it on to the students.
Yeah, yeah. In fact, I would send Sham Series'. I think I have sent that book already to you. Sham Series' book.
Yes, sir. Tomorrow, with the end of classical dynamics, we would then to the persistent learners
Sham
and
Series
attendees.
is.
Yes.
If I have not sent, I will resend that book. Where we have a lot of problems, because Sham series books are usually full of problems. So a lot of problems on Lagrangian formulation, a lot of problems on Hamiltonian formulation.
Yes, very true, very true. And if the students want further explanation or something, we'll see how to fit in. If another hour is required with you for a doubt class, or a class where they can ask their doubts, we shall see as much as possible. But you shall be teaching a portion of EMT also with us, along with Dr. Rachna. And so that will be also quite enlightening.
Yeah.
So thank you so much, sir. We are really grateful for this today's
My
lecture,
pleasure. My
and we look
pleasure.
forward to tomorrow's lecture also. Thank you
Thank
so
you,
much,
sir.
sir.
Thank you so much
Okay.
for
Thank
having
you.
with
Thank
us.
you.
So,
Right.
Dr.
Thank
Divya,
you.
please flash tomorrow's slide and
Yes,
share
ma'am.
it
Sure, ma'am.
with the students. Students, as you can see very clearly, the attendance link is on the Zoom webinar chat. It is being repeatedly posted, and you are requested to kindly fill up your attendance. And please be fast so that we can end the meeting. Dr. Divya, yes, tomorrow. So tomorrow, the 2nd of August, we have Electromagnetic Theory, Polarization, 2 hours lecture with Dr. Sanjay Kumar, who taught you today, and the concluding lecture of Dr. Partha Goswami in Classical Dynamics, which you just heard our discussion with him. And you were requesting for yesterday's PPT and today's PPT. Dr. Partho's PPT will be shared with all those who have attended the lecture today, and the rest of it will be uploaded on YouTube. You have to just wait for a day. That's it. And please be attentive towards your email addresses. We will be giving you updates there. And in the coming week, probably we will be having only a consistent group of students who will be entering into the Zoom webinar, and probably live streaming on YouTube may not be possible, or we shall see as per the decision of NASI, right? But all the lectures will be uploaded on YouTube later for wider viewing. So please stop the recording, Dr. Divya, and I would like to thank my entire organizing team, Dr. Pushpa Bindal, my co-convener, and all others. Please switch on your